Alrighty, welcome back. Let's go ahead and take a look at numbers 36 through 40. 36 reads, Alex drove at 70 miles an hour while Bill drove at 55 miles an hour and took 43 minutes longer to make the same trip. How far did each person drive? Well, the important thing to note is that their distances are the same. And again, we're relating distances and times to speeds. So, distance of Bill equals the distance of A, so dB of B equals d of A. That's my notation. And distance is speed times time. So the time that Bill spends moving times the speed is going to equal the time. What was his name again? I already forgot. Alex? No, sorry. Yeah, Alex. I apologize. Alex times their speed. And so Alex's speed is 70 times his time t. Bill's speed is 55. And his time is whatever time Alex spent, t, plus an extra 43 minutes. But because our speeds are in hours, we want to convert these times into hours. So the 43 minutes over 60 plus t, that's going to be in hours. From this point, either end solve or do a little bit of algebraic manipulation. For instance, here I would do 70, enter, 43, enter, 60 divide, 55 multiply, subtract that over from the 70. Then over here, I recognize that the t is going to be 55t minus the t, divide that over, and now we have our time. Alrighty. Take that time, multiply by 70, and then now you know how much they traveled in miles. Then multiply by 1.6 to convert the answer to kilometers. Alrighty. 37. A line crosses the x-axis at a certain point and the y-axis at another point. And they want us to find out what is the distance from the line to the origin. Now, this question can seem a little intimidating and tough, but with enough geometry, it's quite manageable. But we have to understand a couple of concepts, especially what do they mean by distance of the line from the origin? Because to me, initially, that just made no sense. So give me 1 second so that I can fire some things up, and then we will talk about what's going on. All right, let me go off to this space and find our graph. So here is our graph of the problem in question. Happens to have, again, an x-axis, or crosses the x-axis at 10.9, and the y-axis at about 10-ish. And I forget the number, but we'll get that here in a second, because it will be necessary. Now, the concept that I wanted to talk about that is important to answering this question is, what do they mean by distance here? Because here I happen to have a line going from the origin, and there's that distance right here from the origin to the line. Here's another distance. Heck, here's another distance. And another distance over here. Now, I apologize, but it's not, at least graphically, things aren't working out. It's destroying the line. Now, it turns out that when they mean the distance here in a problem, the shortest distance is going to occur when the line representing the 2 points here, which I'm going to redraw in green because apparently it's disappeared, but when the line connecting the origin to that side here, that's going to be perpendicular. So that's actually going to make a right triangle. And so I'm going to try drawing another right triangle to kind of explain that in a little bit better detail. So I kind of redrew it, and I probably should turn off ink to shape. But the question is asking us for this distance here, and that distance is going to be perpendicular to part of this line segment. Now, in simpler problems, it turns out that this line segment would be the midpoint between 2 points. But that would only occur if the 2 points are the same distance from the origin. Okay? In this case, all we know is that this distance down here is going to be the 12.9, and we're trying to find a certain angle here. Because if we do a little bit of trigonometry, that 12.9 is our hypotenuse, and we can say cosine, tangent, not tangent, my goodness, I'm all over the place. sine, because here's our angle and this side is opposite. So sine of this angle here, that's going to be equal to the distance in question divided by 12.9. Now, how do we get this angle? Well, it turns out this angle is going to come from our right triangle originally with the 2 points. Because we're going to have a right triangle with a height of some amount 10, some round of about 12, and the two sides are related through tangent, so tangent of that angle is going to be the opposite side, which, give me 1 second, I'm going to try and find out what its value is. .5. So it's going to be tangent of of the angle is going to equal 10.5 over 12.9. To get the angle, we're going to do arctangent of those two numbers divided by each other. And so once we have that angle, we take sine of that angle, we multiply by 12.9, and that's going to give us the distance from the line to the origin. And again, the trick to answering this question is recognizing that this line here is going to have a variable distance, and the optimized distance occurs when it is perpendicular to the slope of this line. Now, we don't need to know the slope of that line exactly, but its slope is determined or characterized by that angle here. And so again, we use the two lengths, the 10.5 and the 12.9, to get that angle, recognizing that this is going to be the hypotenuse of this upside down triangle here, and this side here is going to be opposite the angle that we just found. We do sine is equal to that distance, opposite, over the hypotenuse, 12.9, move it over, and there's our answer. Alrighty, let's go ahead and continue with this really lengthy video. Okay, next question. The United States flag is 3 feet 10 inches tall and 5 feet 9 inches long. It is mounted at the top of a flagpole, so that the tip of the flag is of the Drew flag is 12 feet off the ground. The question is, how tall is the flagpole? Okay, so to answer this question, we need to be able to do a little bit of geometric modeling of this flag. Now, when the flag is fully splayed out, the top part would be all the way over here, and they tell us that the dimensions of the flag are 3 feet tall, 3 feet 10 inches, and 5 feet 9. So 3 feet 10 out of 12 inches tall, and 5 feet, man, and my memory is going down the drain, 5 feet 9 inches. And I knew it was 5 feet 9 inches, but I was hesitating. 5 feet 9 out of 10, 12, sorry. Okay, now when the flag is no longer billowing, this is all going to hang down, okay? And so the top of that is the whole flag is going to hang all the way down here. Now, because of the geometry of the way this flag works, it's going to stay tight or rigid. It's not rigid, sorry. But it's going to fold in such a way that the part that's going to stick out the longest is essentially this part right here. There we go. And my arc doesn't look very good. Let me try drawing it again. But for instance, the top of the flag is going to make that portion there, and the bottom of the flag is going to swing down some extra bit here. So the lowest part of the flag is going to hang down some distance. Now they tell us that this total distance here is 12 feet off the ground, and then the flag is going to be this extra distance, not drawn to proportion. So the idea is that this length right here, which is the Pythagorean theorem applied to the two lengths, right? So the 3 feet 10 inches. Excuse me. Squared plus the 5 feet, 9 out of 12 inches, quantity squared. All of that is going to be L. And so it turns out that the height of the flagpole is going to be the 12 feet plus the length of the diagonal of the flag. And so from there we were able to get the answer. Alrighty, next one. Oh man, 39 this year has been really interesting. It's been a little bit more involved than the traditional just apply Casper Tatusa. And I appreciate that because these questions have gotten kind of boring in my opinion. But they're challenging and they're not as straightforward points these days. But let's go ahead and take a look at 39. So they want us to find the radius of this inscribed circle. So the circle's inside, so C, and that's going to be CASP, or area of the triangle, over the semi-perimeter. Now, how do we get the area of this triangle? Well, the problem is we don't have the base and a distance that's perpendicular to it. We don't have the height, so we can't do 1/2 base times height. This is where Heron's formula comes into play. And Heron's formula requires us to know all 3 sides of the triangle. So the first thing we're going to want to do is find this side here. Now the convenient thing is that we have enough information that we can write law of cosines and get this side right away. So the idea is that law of cosines, right, it relates a side and the angle opposite it to the other 2 sides. So in this case, with law of cosines, what we could do is 62.9 quantity squared, right? It's going to equal the 92.5 squared plus the unknown side, which I'm going to call a squared. And then we do minus the 2 sides multiplied, 92.5 times a times cosine of the angle that we're opposite of 35 degrees. And so from there we could solve for a, throwing it into the solver. You know, by now, hopefully you have law of cosines programmed into your calculator. You could call it as, you know, LOC, and you feed it the arguments, the unknown side a, the other side 92.5, and the angle, that's the way I have mine programmed, takes in 2 sides and an angle, and it's going to be equal to the other side, square rooted technically, but you can program it your way. Anyways, you have it solved for that side length a. Then the last part for CASP is that the radius of this triangle is going to equal the area of the triangle. Sorry, the radius of the inscribed circle is going to be the area of the triangle over the semi-perimeter. And again, the area would be with Heron's formula, which is going to be the semi-perimeter, the 3 sides added up, divided by 2, times the semi-perimeter minus A, times semi-perimeter minus B, times semi-perimeter minus C. And again, in my opinion, it's very handy to have this guy programmed into your calculator all over the semi-perimeter. If we don't, please see me. Let's program these in. Let's get them going because these are easy points if we can just code them in. All right, 40. I've been going over this question countless times. There are so many ways to solve this guy, and I'm trying to think of the fastest way. And I think I got the fastest way, but we'll see. Actually, the fastest way does not involve all this stuff off to the side, but it does involve about half of it. Okay, so they want us to find this unknown side. The good thing is that they give us a fair bit of information. For instance, we can start off with recognizing that we have a supplementary angle between these 2 angles here. So 180 would be equal to the unknown plus 68.5. So we solve for it, and that's 111.15. We'll see if we need to use that later, but just in case. Alrighty. So what's the first thing I would do? Well, we have this angle in this side and this side. Maybe a fool's errand, but let's find out this angle alpha using law of sines. So, setting up law of sines, sine of alpha over 9.5 is going to equal sine of 68.5 over 11.3, which is what I have over here. Solving for that, we get an angle alpha of 51.46. Now that we have 2 angles in that triangle, we're going to solve for the third angle, which I'm calling beta. And so 180 minus alpha minus 68.5 would be equal to beta, And so we find out that it's 60.05. Alrighty. Now that we have this angle, in my opinion, you can go around and start solving for the other angle, gamma, and then delta, and then do a law of sines to find this side here. That's about 3 more steps, I believe. Another way we could technically do this question is recognizing that once we have this angle here, beta, we have this side, part of this side, and this side. And then we can do another law of cosines. And so I would say law of cosines, 14.9 squared is going to equal, the 11.3 squared plus this other side down here. This other side down here, I'm going to write it parenthetically as 9.5 plus x, quantity squared. Then comes the next part of law of cosines, minus 2 times the two sides, 11.3 times 9.5 plus x, times cosine of beta, which we just found, which was 60.05. So I think this question ends up being a little bit faster that way. We don't need to use the 115 or the 111.5, sorry. And it's really just 2 steps with a really nice simple geometry, right? We're able to do a little bit of the law of sines to get that angle. Once we get that angle, we get this other angle, 180 minus the 2 sides, right? Simple geometry. And then we can do a law of cosines. The challenge here is knowing your law of cosines. Alrighty, so that's it for these. We'll continue with 46 through